Hello. Lorenzo, you must be exhausted. Was it a productive day yesterday?
Sorry, didn't catch that.
Was it useful to yesterday?
Oh, yeah. It's very, to me, it was very useful. So for is both for refreshing on the previous model that are already building and to create a new one is very useful. And Jonas is, I think, is having a lot of fun. So really good.
I know this isn't the easy, maybe not the best way. Best way to build models is to try to do it in a hurry, but it's an interesting experience, I think, in its own way.
Yeah, well, perhaps it's more about doing something fast, trying to make something work, and then if one want to elaborate, sits down for with a little bit more of calm and perhaps contact you back later if there are some details that are not really there.
And we've had a really good experience in our group and everything. Everybody's feeling like they've learned a lot, and trying to get this, model working is a good way to like really, let it sink in a little bit. And then we're planning on coming back and meeting, after this to try to get it, up to like maybe a publishable unit or something. So.
Right. Well, I mean, it's a lot. These models are inevitably very complicated. And so it's not something where, sorry, I just got the breakout room set up. I suspect a lot of people will not be here today, but I'll
Go ahead and stick them somewhere.
sorry, I just put them in case. There we go. Okay, so that's done. So we have breakout rooms created. We have everything set up. Okay. And the one thing. Just give me 1 minute here. All right. So yeah, it's you need to unwind a little bit after this. Perhaps it would make more sense to do the hackathon separately from the training part of the workshop. Usually it's harder for people to, if they're going to block out some block of time, it's probably easier for them to just make it longer than,
Yeah, instead of having like a Monday, Wednesday, Friday or something that just drags it on forever. Yeah. Yeah. I think,
as I say, last year we did the 4 days of classes and then 3 days of hackathon, but we were barely able to cover the material we wanted in 5 days. So
yeah. There's a lot to learn here. That's for sure.
so tell me about your background. I know somewhere in the documents it's there, but I'm sorry, I don't know that.
Well, I have an undergrad in biochemistry, and then I became a classroom teacher. I taught high school and middle school for many years, and then decided to go back. So got my PhD in cell model, and just finished at UC Davis a couple years ago, and then we moved back home to Texas to be closer to family, and I found this position here with Michael Sachs at UT, and so I'm kind of the resident biologist, and most of the other people in the lab are like, super hardcore programmers. So
you're the interface. You're the interface between the real world and the computer.
Yeah, exactly. So
did I ask already? Did you know Mark Alber at Davis?
no, I don't know him. Mm-mm.
So he set up a computational biology institute at Davis.
Oh, okay. Yeah. I wasn't really on the computational side at all. I was a total wet bencher. So I was in the pharmacology department. So I mostly interacted with all those people, Don Burrs and that whole group.
Well, pharma uses a lot of modeling, but they have their own. I mean, PBPK is its own world.
Yeah.
And then molecular dynamics. So you've got these two, the biggest scales of the smallest scales and nothing in the middle.
Yeah. It seemed like most of the people there were quite a few modelers, but they were kind of on the same, they were more like on the physical dynamic side of the heart than they were the actual, like, dynamics of the chemical theory. So yeah. So
well, cardiovascular modeling is its own field.
Yeah.
It's very, very developed. And it's the one place where the kind of mechanistic modeling is really used. People, heart surgeons design surgeries using models of specific patient hearts. Not all of them and not all of the time. No. And I was blown away a week or two ago. HeartFlow, which was a company that grew up out of mechanical heart cardiovascular modeling at Stanford, raised $400 million in an IPO.
Wow.
Now they already have an FDA approved diagnostic,
yeah.
which took them 15 years to get to.
Mm-hmm. Yeah.
But and what they had to do to make it go from the kind of exploratory simulation that we're doing here to being a medical diagnostic is we had a talk by their CEO, and it's really interesting to see. I mean, it's not an easy thing to take things out of the lab and get them into the clinic, but it was quite impressive to see that.
Yeah.
And I think there are a lot of those opportunities, but it's a big job.
Definitely. Yeah. But yeah, so that's what we do in our lab, is work on different models of the heart. I'm working on the heart valve, so it was really good match with the guys in the group that I'm in with this study too. So worked out well.
So I think I mean, the heart tends to be sort of special because you have, I mean, the myofibers are fundamentally different from anything. Muscle fibers are muscle fibers at some level, but they're different from the other kinds of tissue. And you have the complicated electrophysiology, the complicated mechanics, and then you don't have much cell rearrangement. And so a lot of the heart models don't even have cells in them. They jump directly from ion channels up to the contractile behavior of bulk tissue.
Yeah.
I always think of Andy McCulloch at UC San Diego, who does a lot of very sophisticated heart modeling.
Yeah.
There's certainly many groups like the ones you're involved with that do all sorts of wonderful heart modeling. It's a special world, just the way the people who do neural modeling have their own world.
Yeah, exactly.
It's interesting because the heart modeling community, the neural modeling community, and the everything else community that we're part of is smaller than either of the other two.
Well, I think of cancer as kind of a third group that it gets a huge portion, like attention, I guess.
Right. Well, the kinds of things we do are definitely used in cancer modeling quite a bit. The other thing that's done are larger scale continuum models. So modeling, after all, in a sense, every radiation therapy is designed in some way. There has to be a computation to show you where you irradiate, what your margins are, and these kinds of things. And so those kind of classic radiation therapy models are one of the earlier ways computers were used medically.
Mm-hmm.
Sort of mechanistic models were used medically. And there have been a couple of papers published using GEANT, which is a radiation code, coupled to CompuCell. Probably needs to be done in more detail. I was just seeing some papers, recent papers, a couple other modeling methodologies that way. Mm-hmm. That's a sort of GEANT's a big radiation dosimetry model. So in principle, you can then calculate radiation dosimetry in the tumor, kill cells or have them mutate depending on the radiation dose. The difficulty with doing that is, like most of these very detailed simulation methods, it's slow. GEANT's very slow. Mm-hmm. And so if you have to resolve the problem every time step, the CompuCell side is faster, but the radiation models are pretty slow. Mm-hmm. But it's certainly worth doing. Another thing that we haven't really explored, which the HeartFlow people are doing, is the idea of artificial intelligence surrogates. I mentioned that very briefly sometime during the talk, one of the talks where you, for example, of course, image segmentation is the classic neural network machine learning AI problem. And that's certainly revolutionized our ability to do segmentation. Sure. But in principle, if you have a network, a complicated network like some of the people in this group have been talking about, where they have 500 components of molecular species.
Whoa.
You can train an AI system. If you only care about a few inputs and outputs, you can potentially train an AI system to learn the correlation between the inputs and the outputs, and then speed things up a lot. And the cardiovascular people usually use these very elaborate solids modeling frameworks. again, I'm always joking about abacus. I don't even know if abacus is a big methodology anymore.
It is.
10, 15 years ago, it was the big solids modeling package.
Yeah,
And
we'll use it.
yeah,
Yeah.
but
Our
it's,
use it.
go ahead. You use it? Yeah.
Our
But
lab
it's,
uses Phoenix.
so you use which? Phoenix?
Phoenix. But
Phoenix,
there's
yeah.
people still use abacus. And there's
Well,
times when Phoenix, there's some things that
yeah.
Phoenix can't do yet. So.
Well, we should probably try again to couple CompuCell to Phoenix. As I say, the problem with it when we did it the first time was that they wouldn't let you run it on Windows.
Oh yeah, it's still a little bit janky on Windows, but I have it running on Windows.
Okay, well, did you hear that, TJ?
I did. It can be done.
It can be done. It can be done by Tony. So
Well, we should ask you because at the time, a long time ago when we did it, Monte did a port to Windows, and they were very hostile to it. There was sort of political belief that it shouldn't run on Windows, and so the developer community was rather hostile to that. Maybe, but if they're more open-minded, Phoenix is an amazing package, and having that coupling would be really great.
Yeah, they still prefer using Mac, that's for sure. But you can get it going on Windows now.
Well, Tony, when I run into issues, I know who to call now.
Okay. I'm not gonna say I know how to solve that problem, but I usually have to go running to someone else. But I guess I know who to call.
Okay, well, today we don't really have a very, thank you everybody for coming back. I want to appreciate everybody for your endurance and coming back for the 8th day of the workshop. I've recreated the breakout rooms from yesterday. I realize that some people may not have be here, but the excess breakout rooms don't do any harm. And so we really have a very light agenda today. The agenda for today is to work on the projects and to help each other out. And so I thought we would take a few minutes at the beginning of the day to check in if people had ideas, progress, problems overnight. That can be pretty quick. And then we will have people work with the systems. And then we'll do another quick check-in around 1 p.m. and work again. And then I'd ask people to try to prepare a little report on how far you've gotten for 5 p.m. And that will be the of the meeting. Jim, I see you're there. TJ, do you have any announcements or comments that you want to make before we get started?
I don't have anything.
Okay. Okay. Well, I guess I'd like to go through the sorry about the flipping slides there. I'd like to go through the groups and simply ask. I don't know. Some people, the hackathon spirit typically is people stay up all night working, but I don't expect that people would have done that. If there's anything people want to go over this morning, people want to go over this morning. Well, when we did our first COVID viral infection and immune response model, we did it as a 3-day hackathon for some commercial outfit that was sponsoring hackathons, and we pretty much stayed up for 3 days. And by the end of the 3 days, we had a model that wasn't bad. As I've said, it's not philosophically, it's not the way I think modeling really should be done, but it's a good learning experience, I think. So why don't we just go down the list and see who would like to report. And if you don't have anything to report or you don't want to report, that's fine. But we should go through the teams, and a few people are still signing in, and then we'll separate and begin to work. So who would like to start out and give us an update? Tony, do you want to update us? And again, it's fine to just say we haven't done anything since yesterday, but if there are any issues, or maybe to say what your goals are for today, that might be a helpful thing.
Okay, so I'm in Javid's group, and Nasheen and I are working with him, and we're working on a model of calcific aortic valve disease. During that disease, there is a transition of the endothelial cells into mesenchymal-like cells, and they become highly activated and produce a lot of collagen, which causes problems. And so we're trying to model that. And so yesterday we started with a model with 10 cells and a bunch of collagen and a field of TGF beta. And we were trying to get the
Saeed.
hi. And we were trying to get the field of TGF beta to interact with the endothelial cells using the antimony to then cause that to have like a black box conversion into alpha SMA, and then the alpha SMA to accumulate in the cells, and the endothelial cells to also chemotax towards the TGF beta. So we ran into some issues trying to get the antimony going, and that's where we kind of left off yesterday. So today we were planning on kind of paring down the model to just a few cells and less of the collagen, and see if we can get it working the way we think it should be. And then if we have time, scaling it back up.
Okay, that sounds like you got through a lot yesterday already.
Yeah,
if you're building a model that complex in a day.
Yeah, Javid had done a lot of work already, so that was great place to jump off from. Yeah.
Okay, and I'll be happy to join teams and work out. Lorenzo. And if I'm duplicating a team, it's okay. I'll just go through the screen and.
I think Jonas can talk about the group, the cancer bit that we have done.
Okay.
Hi, yeah. So for yesterday, we were just mostly working on sort of assigning the different attributes to the different cell types, like what we would want our mitotic cell to behave like, and like adding some of the various cell types. And then today, I think we will try to implement those behaviors into the maps of the biopsies that we have. And I guess I can I share an image? Or?
Sure, of course.
It's really just a screenshot. I don't really have any.
That's fine.
Any slides prepared. All right, can you see this?
It's just starting. I was going to say for this afternoon, at the end, if people could try to prepare a couple of slides or a screenshot or two or a movie, and maybe a one slide summary for the 5 p.m. final report, that would be great. We don't have anything formal. That would be really helpful. Okay, this is great. Tell us about it.
All right, yeah. So here we have our proliferating cells in purple, and as they start to grow, they do become, after they divide, they become quiescent cells, but a small percentage of them will have a chance to become mitotic again. And then every sort of 100 steps, we introduce, like we simulate radiotherapy, where the cells have a chance of dying. And if you are a proliferating cell, you have a much higher chance of dying than if you were a quiescent cell. And once they become a necrotic cell, which are the ones in orange, then they start to produce release chemokines, which our lymphocytes will be attracted to. And you can't really see that there were originally 3 lymphocytes, but they've kind of been buried and all that now. So yeah, that was kind of what we were working on. And today I think we'll try to introduce like the tumor cells secreting a chemo repulsion molecule. Yeah, that will be, and then integrating this into the H&E biopsies.
So the chemo repulsion would be to represent a immune hiding or immune avoidance.
So I think in like tumor cells, they can secrete like PD-L1, which is a chemo repulsion for lymphocytes.
Great.
That's all. Thank you.
I mean, as I was saying to Tony earlier, people have tried to couple CompuCell to some radiation dosimetry simulations, and so it's. I don't think that it got to be very sophisticated, but it's a great idea. Okay, right. Farnoosh.
Yes, hi. Today, Carlo will explain what we did yesterday.
Can you tell us just a word or two about it? What you got done yesterday?
Yes, Paulo will explain that.
Oh, Paulo. Okay, sorry.
Yeah. Can I share my screen?
Please go ahead.
Okay. Can you see it?
Yep. That's great.
The simulation on the 4 screens of the simulation. Okay. So basically, what it did yesterday, we tried to start implementing the cancer growth, like a small tumor, and some immune response regarding some cells dying by a given intervention, and they release some molecules that attract the T cells. So the first step was to get a tumor that grows into a stable size, and we did that aiming at that the cells will grow based on an oxygen field. So when it's there's a low concentration, they will grow and divide less. So cells at the border tend to become larger and divide more. And eventually, with the low concentration of oxygen, cells will start dying. These green cells are apoptotic cells, so they'll start dying. So these dynamics should create a tumor that grows into a certain size and stay stable on that side. And then at some point, that here will be at 900, we introduce like intervention that could be like chemotherapy or something like that. And some cells will become necrotic, that will be shown in blue. And these necrotic cells release DAMPs. There are molecules that will attract immune cells. And when this concentration reaches a certain level at the border of the simulation, some T cells will start popping up, and they'll be attracted by the gradient of these DAMPs towards the tumor. And this gradient will eventually disappear. And that's what it get into now. And the next step would be like to introduce the IL-2 response from T cells to tumors and make them die and attract more T cells and so on. Like, this is not realistic, the numbers here, but it's just like, we just get the behavior and then we can tweak the parameters.
So one small thing which I'll mention because it could have been useful for everybody. I don't know when you're doing the chemotaxis of the cells, whether you're adjusting the chemotaxis parameter based on the concentration. Did somebody show you how to do that? Because what tends to happen is either the chemotaxis is very slow because the chemotaxis parameter is too small, or it's too strong, in which case the cells fall apart. And so the simplest thing to do is to adjust the chemotaxis parameter by them. Okay, so then you have to specify the chemotaxis in the Python, but you adjust the chemotaxis parameter by the mean value of the chemical field. So you have a lambda 0, which is the ideal chemotaxis parameter, and then you divide that by the local concentration of each cell for each cell, and then you can have a much stronger chemotaxis with it's effectively modeling adaptation of the chemotaxis receptor
without the shear of the cells, right?
No, and it's something we should probably have built into CompuCell, but we didn't. But in the past year or two, we used it almost all the time, and it helps a lot because then you can make the chemotaxis much faster compared to other things, and then the simulation runs better. So ask one of the people. PJ knows how to do it. Jim knows how to do it. I know how to do it. Giuliano does. So let's we'll try to help you with that, because I think that, I mean, it's a small thing, but a lot of people probably would benefit from that. Great. Well, that's a lot of progress. Great. Okay, Tarim.
Hello.
Hello.
Hi, I am from Pernoscript, and we collaborated and did this work together.
Again, if somebody's already spoken from your group, you don't have to speak again, but I just want to make sure that everybody has a chance if you would like. AJ.
I just came back from the break room, so I haven't actually had a long discussion with either Kato or Abhishek, but we made good progress yesterday, particularly what we discovered towards the end of the day with some interactions with Giulio is that there are already many elements that we would like to incorporate into our model, which were in the wave example in the student materials, where the constrictions don't just happen everywhere at the same time, but they start from the back and progress. And when you have it in a wave, it organizes the segmentation in a much more organized manner. And this corresponds to actually what happens in the real primordium. So Kato is working on that. I just visited her in the break room. It's still a little bit buggy. So she said she doesn't have anything to show at this moment because she's still working on the code. And Abhishek also had some good help from Giulio in making the cells with 3 parts to get the constriction working based on that sort of framework. And he should be on here. I don't know do you want to add anything, Abhishek?
Yes, so we actually compartmentalized those cells and added, like in Giulio's model, we have added those FPP links, the apical site. So those cells are then now coming together and forming a more epithelialized structures. And now we also want to see whether, the models which we were working on yesterday did not have an upper boundary, which is the skin. So I also want to see whether having the skin would also, can it be implemented or not? Can I do it or not? And another thing, as Ajay already mentioned, whether in a wave we can actually implement these different patterns of rosette formation where rosettes are forming. So that would be another nice thing to implement. Yeah.
Great. Well, I'm glad that I'm glad Priyam was able to join us for an hour or two yesterday, because that was her PhD thesis work.
Yes.
I also have a little bit of a request for you, possibly, which is the heart group that we started out hearing from today. That wanted to learn a little bit more about how to do compartmental cells. And so since you've got the compartmental cells running, if you could, maybe one of your group could visit them and give them a 15-minute crash course in how you learned how to do compartmental cells, that would be great, because you've just learned it. And the problem sometimes for us is it's not obvious to us what's difficult and what's hard, what's easy, because we learned it a different way. And so if you've just done it, that would be really kind of you if you could do that.
Yes, sure. Which group did you say?
Heart.
So that's Tony's
Okay.
group.
Okay.
I mean, I don't want you to take too much time away from your own project, but I think learning from each other is an important part of it.
Sure. No, I'll be happy to help actually.
Okay. And they've already jumped out into their the group is called ENDMT, endothelial mesenchymal transition. And
Okay, so then I'll also probably join the group for some time, and maybe
if you're willing, that would be very kind of you.
Yeah, sure. Thanks.
Okay, so let's see. Just keep it going down the list. Marco.
Yes, here I am. Good morning. So yeah, yesterday was a really productive day, and I continue to develop my model with my boss. I can share my screen so I can show you what I did up until now. Okay, so this is as always my usual configuration with a bunch of cells in the middle of the extracellular matrix. The cell types change according to the Mabos network, which is this one here. I linked a couple of more nodes to the CompuCell code. So, for example, these couple of hours before, I managed to link the amount of oxygen concentration to the oxygen node, which is this node here. On my list, I still have to link the extracellular matrix sensing node. Problem is that I don't want to sample the field in the center of mass, but in the boundary, so at the boundary of the cell. So I'll probably use this function with pixel list to check the pixel around each cell. And then I noticed that I did a little mistakes yesterday. So basically, this function right here that links the CompuCell 3D inputs to the Mabos network was in start, and so basically it wasn't. This function wasn't updating Mabos at every step, but just at the beginning. So I just moved this in step, like right here. And I encountered a little problem. So right now the simulation is a bit heavy, computationally speaking. So I think instead of updating the Mabos settable at every Monte Carlo step, I think I will update the network every, I don't know, 10, 15, 20, I don't know. I have to do some tests. And another thing that I add is the pressure value. Each cell should sense a certain amount of pressure that I define like the target volume minus the cell volume. And if this pressure is above a certain threshold, which right now I put just 0.5, absolutely random, but I will do some parameter fitting in the next days, this will trigger some DNA damage. Trigger the DNA damage is pretty important because this could activate the pathway, the p63 pathways that could lead to apoptosis. And I linked the apoptosis node to the deaf cell type, and deaf cell type is linked to the deaf steppable function. So when apoptosis is on, it will trigger death. I thought that I can do this also for hypoxia, because right now I don't really care the kind of death, but since this Mabos model foresees different kinds of death, like apoptosis, autophagy, hypoxia, anoikis, etc., maybe I can link also hypoxia and autophagy to the death steppable function. But this is something that I will look at this afternoon. And yeah, that's actually it.
I mean, I think breaking things up into multiple steppables is good practice, and I tend not to do it. I'm lazy that way. I mean, one thing, of course, eventually is you might have different kinds of death, and the signals that are sent are different. So a necrotic signal is different from an apoptotic signal, is different from a periapoptotic signal.
Yeah.
Since that's great. And so the thing that's heavy is the MABOS in your simulation.
Yeah.
Yeah. Okay. Well, that's a trickier one, because that one we don't own that code. So accelerating is for people in general, for the CompuCell side of the simulation. Remember that if you're on a multi-core machine, you can accelerate by just changing the number of threads that run in the CompuCell simulation.
I already did it. I have 10 core setted.
Right, but that won't I don't think help with. I don't know if MABOS is parallelizable in that way. In principle, it ought to be, because if it's running independently, if you're running independent replicas, you ought to be able to run them in separate threads. But I don't know how the implementation works. That may be something we still need to work on. But
No,
that's
actually,
great.
I just realized that I can, in the configuration file of MABOS, I can actually set the number of core. Yeah, I have to do it.
Okay.
Thanks for
Great.
the idea.
Okay, Janos.
Hello, everyone. We are in the state that we were in yesterday. So we have the cell types and the gradients, and now we have to scale the gradients to achieve some believable behavior, and then set up the gradient-dependent rules of the simulation.
Great. And again, if you're having any issues with the mechanics of subcellular buckling and things like that, the lateral line team has been doing that too. One thing is we have several groups working on cancer simulations. We have several groups working on things related to subcellular elements and buckling. And so I encourage people to visit, spend a little time visiting the other groups and seeing if there are methodologies or ideas you can learn from each other.
Okay, sure. Thank you.
You don't have to, but there are more of you than there are of instructors, and so and different people. Some people have made good progress in some areas and maybe struggling in others. So helping each other is a good. So I would encourage you to talk a little bit to the lateral line people and see if they maybe can help if there are any issues. If you're not having any issues, then you don't need that. But if there are, please go ahead. Itamar.
Well, as you know, I'm technically impaired, but I developed some concept that is similar to TJ yesterday. Wonderful progress. Do you hear me?
Yes.
You hear me, because I hear some noise in the background. Anyway, so that concept I have to solidify, and it has to do with the parameters, because I'm hooked conceptually, as you know, about the parameter issue for a long time now, much beyond this, much before this wonderful workshop. So there is no real progress. I have to, because of technicalities, I have to work on the conceptual level, and that's becoming like philosophy. However, the approach that TJ reflected yesterday so wonderfully brings me to thinking about recursive concepts to incorporate in programming and systems like you guys are expert in. But this recursion is mathematical, and it can be adapted to this big puzzle of parameters. So I don't know if this is a progress, if this is making sense. This is Sunday morning. It looks to me like I lost some hour. I thought it was 9 o'clock, and all of a sudden I look at my cell phone. It's 10 o'clock. Oh, I have to connect to James. So here I am. You have questions about it? I will work on it and communicate to you whatever I find, of course, and you can then communicate it to the whole group.
Great.
Okay? Because I'm so impaired that even I don't go flexibly to the Slack. So TJ, I asked him at the beginning last week some question. I didn't get an answer from my emails.
Uh-oh.
And this is about time series, any time series. And he wrote some preprint and he put it on the chat, but my chats are kind of lost or not accessible or not clickable. And so you don't want to hear all my troubles here in public, but I exposed some of them, but I'll still connect to, and also Julio's yesterday gave me some inroads to my big puzzle about Git and GitHub, and I'll bug him later after the workshop because you guys are busy and focused on very different target.
Okay, well, it's good. Always the more perspective we do these, the better. So appreciate your being willing to stick this out and make suggestions from a different point of view. The diversity of the community is one of the things that's most valuable. So I appreciate that.
Can I ask in public a very, very naive question?
Please.
I used to work on Monte Carlo and struggle with quasi-Monte Carlo and random number generators and so on. And maybe somebody can give me one line explaining why Monte Carlo is used here. Very naive and terrible, idiotic question.
Okay, so the Monte Carlo is the deep into the Potts algorithm. And originally the Monte Carlo, and I'll do this very briefly, because it's actually quite a long story. It's discussed in some detail in that reading in the student materials readings folder called From Magnetization to Morphogenesis, which talks about the physics. So these Monte Carlo methods were originally designed to evaluate what physicists call partition functions in statistical mechanics. And they were developed actually as part of the Manhattan Project in the Second World War. They were trying to evaluate equilibria when the actual analytic calculations were impossible. The observation that you could do dynamics with them, which is not what they were intended to do, was made by a group at Exxon Research in those days, Gary Grest, Anderson, and Sorolovitz, who realized that you could simulate boundary migration using these methods, these stochastic methods. The stochastic methods that we use are the Monte Carlo methods that we use are slow in some ways because we reject most of the updates that you try, but they have the advantage that they're numerically absolutely stable. They're unconditionally stable. And they're also quite simple computationally compared to doing finite element calculations. And so we started using these stochastic methods because they were easy to implement and they were numerically very stable. They've become very popular. But the advantage of them, again, is their simplicity and their extensibility, because you write things in terms of these Hamiltonians, quasi-Hamiltonians, and then add them up to get behaviors, cell behaviors. The disadvantage is that you're on a lattice and that they are not as fast as some other methods. Although if you actually look at the world, there's no free lunch. And so the deterministic methods often are not a lot faster because you wind up having to use very small time steps because of stability issues. So that's the sort of a short answer of why there's a Monte Carlo method at the center of everything. The other thing is that the Monte Carlo does in fact represent some biological stochasticity. The way cells move is quasi-random. Now the distribution of randomness isn't the same in the biological system and the simulation, but in deterministic methods, you actually have to add that randomness back by hand. Here, the problem tends to be that you have a lot of control over its amplitude. So I hope that gives you a little bit of background on that.
It's beautiful. Can I get some references in the student material or whatever? Because this is enlightening for me.
Yes. So Giuliano, could you send him the link to that magnetization to morphogenesis PDF?
Mm-hmm.
Okay, great. Suvik.
Hello, can you hear me? Yeah,
Yes.
so yesterday I worked on this polar cell model. So with the collective cellular motion with motile cells. So yeah, so I could able to figure out the external potential, particular external potential for that, and I have implemented that in the Compusel 3D code. And so I have given the run. So you know that they're very long runs, so it will take some time to. But it will be complete by the afternoon session, I guess. So yeah, so I'll give my detail this report there that time. Yeah. So and also today I would like to study some other aspects of this problem, and yeah, let's see. Thank you.
Let's see who's still here. Megan.
Hi. So our group yesterday, we worked on importing the muscle fascicle into our system. And so we had like a histology image that we imported in, and then we started getting like our neutrophils working, as well as getting the dimensionality of like how many planes we would need so that things didn't kind of infiltrate in between. And then today we're working on getting like our satellite stem cells in to help regenerate, get some of the ECM components more detailed and set up, and then also looking at some of the other inflammatory cells, as well as fibroblasts. And yeah, we're still working on debugging. Do you want to share? You can have a teammate share some of the progress and what we are currently working with.
And
So
I would encourage you, if you're having trouble doing the subcellular elements, I would encourage you to talk to the lateral line people who've got those working really well. So I'd suggest one of you jump in and talk to Abhishek maybe into the lateral line, because they've been using a lot of subcellular compartments, and they've learned how to define subcellular compartments in an efficient way. So
thanks. That's a great idea. Yeah, because that's something that we're still kind of working on.
Yeah, so this is our muscle fascicle. It's like a cross section where the red cells are muscle fibers, and there's extracellular matrix all around. And after a couple time steps, we divide those so that we can select a certain number to become necrotic based on like a chemical toxin. And so these are our necrotic cells. And after another time step or two, we should have neutrophils on another layer. These are a neutrophil layer. These little red dots are all neutrophils. And they interact with the first layer to cause some of the necrotic cells to turn into ECM and in a way fibrose. And that's the progress that we've made. And these neutrophils will chemotax along a chemical gradient produced by the necrotic cells.
Wow, that's a lot of progress from yesterday. The last time I saw it, I'm impressed.
Thank
you. One thing again you might want to try when you're doing a chemotaxis is this logarithmic chemotaxis, where you assign the lambda chemo to each cell independently in the Python. And then you adjust the lambda chemo by the mean concentration of the chemical. And that allows you to move as I mentioned before, that allows you to move the cells much faster, even though there are big differences in concentration. Giuliano, you know how to do that, right? So could you maybe join them and show them how to implement that?
And TJ also pasted in the XML to have CompuCell do it in C++,
right?
Which is way faster.
Oh, I didn't know we had it already. Okay.
Yeah, it's new.
Yeah, as of the most recent release, the log scaled chemotaxis is a built-in optional feature, and it is worlds faster.
Okay, so please let people know. That shows that I'm always behind on these things. Okay, okay, great. Is there anything else we can help you with at the moment? All right. Great. Is there anybody? Let's see. Have I missed somebody? I see some people who haven't spoken up, but you have to speak up now. Have I missed a group, or does everybody want to break out and get to work?
Well, actually, I didn't show
Oh,
my
I'm sorry,
progress yet.
Iman.
No.
I'm sorry, Iman. I didn't. Yes, thank you. Please go ahead.
Yeah, no worries. I just made some progress that I wanted to show you and also talk
Great.
about my agenda for today. So if I could just share my screen. Yeah, there we go. So this is the second model that I made, and I exported the simulation, and I just wanted to show you the outcome. Well, I believe CompuCell didn't show the progress fully, but anyhow, this is the VTK file that I got from the second model, and I have a question here. I checked the VTK files and I wanted to know what delimiter you guys used to write the values into the file. Is it a single space or a tab? Do you know what I mean?
Yeah, TJ, you'd have to answer that one.
The VTKs?
Yeah.
It's space, it's not tabbed.
Okay, a single space, great. So my agenda for today is to develop a multi-component agent-based model of cartilage. The components are like interstitial fluid, which is enriched with PG, and then we have free fluid, which is technically free water, and we have collagen fibers. So the mechanism that I considered for this model is that the collagen fibers are linked together, and we have a chemical field which acts like a protease, and it will like digest the PG content of interstitial fluid and convert them into free fluid. So what happens is that when collagen fibers are in touch with free fluid, they tend to push it away and like get closer together. On the other hand, if collagen fibers are surrounded by free water, they will also be digested. So far I managed to like implement the first three mechanisms, but I have problem on the fourth and fifth mechanism, are to like link the collagen fibers together, and also how to count the neighbors of each collagen cell or fiber. I have made some coding in my, well, actually, let me talk about what I used this one to have access to the neighbors, but the compiler threw an error about this function, something about there is no function called like this, anything like, I don't know the exact error, but it was like this, that such a function doesn't exist.
So if you didn't load neighbor tracker,
yes,
it
I
will
did.
throw in it.
No,
So you
actually, I
did.
did.
It
Yeah,
is
yeah, yeah.
there.
Yeah.
Okay, so TJ, that's probably going to need TJ to take a look.
Yeah, but actually I used this function. Let me show you quickly here, if it's okay. This one. Self get cell neighbor data list. And for each neighbor, it seems that I can't run this code, neighbor type. So I don't know how to access the cell type of each neighbor in particular.
Oh, because neighbor is a complex object. It's not, so you're saying type is not defined on neighbor?
Yeah. For each neighbor
think
type, it's not defined.
Yes.
So-
The problem here is that what's being returned by self.get cell neighbor data list at line 36.
Mm-hmm.
The list.
Yeah, it's an iterable. So what you could be getting in line 44, when you try to reference neighbor.type, there's always the possibility that one of the neighbors is the medium, which in CompuCell is none. And on none, nothing is defined. So if you just add, I'll put it in the chat, there's a quick additional conditional that you can add to line 44.
Yeah, sure. But a quick question. I believe this get cell neighbor data list will exclude the medium from the cell type.
No, it does not.
It doesn't?
No.
Okay.
No, because you need to know that you're next to medium and you need to know the area of the contact.
Okay.
So that's a trap. We should probably change medium so that it actually is a cell type. There's a technical reason for that, which is that the parallelization algorithm we use has problems if there's a single cell that's very, very large.
Okay.
And so if you wanted medium to be a cell, then you would have to subdivide it into lots of medium subcells in order for things to work for the parallelization.
Okay. In a sense, I should define like a cluster of cells instead of having a large cell.
Right. And that's a technical thing having to do with the way that parallelization is implemented. And it has to do with what Idemar was asking about, why we have a Monte Carlo method. And that's getting deep into the technicalities of how the code is executed. But if you're a physicist and do statistical mechanics, it's rather interesting. If you're not a physicist, it's not so exciting. But it is an annoyance, and again, it's something that we didn't cover in class because it's time. We didn't have time, but it is important. So TJ, that's another thing to add to our list of videos, probably short videos we need to make. Would be to explain how to deal with medium as a special cell type.
But there is something else as well, Iman. If you bring up your code again.
Here it is.
Get cell neighbor data list returns not the neighbors, but tuples of neighbors and the common area. So on your line 42 for neighboring neighbors, neighbor there is a tuple. No, 42. Neighbor there is a tuple of a cell object and the common area. So it should be for neighbor common area in neighbors.
Like this.
Yeah. Or in line 36, you could do neighbors common areas equals.
Yeah.
And that will divide the two in there. And in that case, you could do for neighbor in neighbors.
Yeah, I need to exclude this one. Okay, great. But it still will throw the error because we don't have this neighbor.type thing, because neighbors are objects, right?
Neighbor is a cell unless it's medium. So you should have that if should be if neighbor and neighbor.type, because Python does the if statement in sequence. So the first will fail and the second will be fine.
We should probably somehow figure out a way to have a trap where if you ask for cell type for medium, it returns medium
Well, actually, I
cell.
defined it as a count. It will count all the cell types around the collagen fiber. And if it's like 8, meaning all surrounding cells are free floyd, then it will change the cell type to free floyd. So I
Well,
have
it's only gonna be 8 if the cell has a face touching 8.
Yeah.
It doesn't count the corners.
Okay, so it doesn't count corners?
Yeah, you need an actual face.
Okay.
If it's a single pixel.
Yeah, if
If
it's a single pixel, it won't. Yeah.
Okay, yeah, you are right. Yeah, you're right. Okay.
So maybe Giuliano, you can work with him and a little bit today and help.
Yeah, that would be great. Thank you, guys. Okay, I will stop sharing.
Okay, is there anyone else we've missed?
Yeah, I think the doctor who was speaking yesterday, the MD, about Finsler space and so on.
I don't see.
He asked you about the Euclidean distance being replaced by something else. And that was very interesting to me, but again, I miss a lot of details. Maybe he didn't wake up yet. You know, doctors are overnight shift.
Well, people are in all sorts of time zones, so
Of course. It's Sunday morning jokes.
Okay, is there anyone left that wants to speak that hasn't spoken? No. Well, in that case, people are already moving to the breakout rooms. Bobby, can we talk for a second since you're here?
Yes.
So thank you for joining us. If you can help out a little bit today, I'd be most grateful. You can see people have been doing a lot.
Yeah.
We did not follow our classic structure for doing model definition because we were shorted on time. And that was probably a mistake. One thing that would be really helpful would be for us to develop just a very short document asking her what we'd like to see in a little report for 5 p.m. today. And I could rough something out. But I think the main thing is that since we've lost some of our assistants for today, if you have an hour or two to go around the rooms and help people out, that would be great. And, that was my main point.
Yeah. I saw a handful of the groups yesterday. They were pretty far along. Many of them had established concepts at least, and that was good. So it seems to be a pretty sophisticated group.
Yes, it's been quite impressive to me how far people are getting in a short time.
Yeah.
All right. TJ and Giuliano, anything you want to discuss today before we start helping people out?
I was just going to ask if you could create a breakout room for maybe me and other instructors to do one-on-one support.
Well, we have that. I created one breakout room called Open Discussion, and we have a couple of breakout rooms that are not being used because the teams aren't here today. So the only problem is that I can't edit the breakout rooms. So if you want to grab a room that's not used, like neurons or smooth muscle or homeostasis, then let me see. I'll try. I don't think I can edit. I can't edit the breakout rooms while they're live.
Okay, that's no problem. Thanks.
But there is one called open discussion. I should probably have made two open discussion rooms, but we didn't use it so much yesterday. So that's what.
Okay, thank you.
Okay. I think Iman definitely would benefit from some help. I think the East team would benefit from some help. And David was here, but he jumped into his breakout room immediately, didn't say anything. So, all right. Okay, and I'm going to need, I want to help. I had promised I would join the, Jim is in with them already. Okay. Megan, what can we do for you?
We were trying to still sort out the compartmentalization. We tried to go and talk to the one group that you mentioned, but they were pretty busy. So I didn't know if anyone else could kind of help out with that.
Right. Giuliano, how could you help them?
Yeah.
Would we be able to jump into your room or a separate room, because our group is currently using the our room to collaborate?
Right.
Sure.
Okay, so we've got a group called Open Discussion for that purpose. We were just saying I should have created a couple of extra rooms, but there are a couple of groups that created rooms and then didn't come. So we have some extra ones, but they're going to have strange names. So but if you like, or you could do it here in the main session too. That's okay.
We can go to the open discussion breakout room.
Okay, great.
Thanks.
Okay, see you there.
Okay.